And can we turn on the record button?
Yes,
Yes.
just did. Thank you for reminding me.
Great, thanks.
So record. Okay, so the outline. So just as a reminder, you know, here's a picture by Tom Rockwell from that 2010 El Mayor Cucupa earthquake. And so, you know, when we talk about strike slip, we're talking about the sort of discontinuity in position of features along the fault that's in the strike direction. So, you know, dip slip would be that goes down the dip. And a lot of times we think about this in a vertical sense. We're talking about strike slip faults because they tend to be pretty steeply dipping, but obviously the fault could have some dip, and then the vertical component is different than the dip slip. So you want to remember some of your structural geology when you think of sense of motion along faults. But for now, we're just talking about strike slip, and so that would be the horizontal displacement in this case of the feet of the two people. And but along strike slip faults, a lot of times we see variable dip slip, and that ends up producing a lot of the interesting topography. So just a couple other things to kind of clean up so you guys have some background knowledge is just, you know, I don't think we've talked about Wells and Coppersmith or earthquake scaling, but you see it a lot in some of the writing from McAlpin. But it's very important that you have in your mind some of these basic relationships. So, you know, this is information based on kind of historic earthquakes where we knew the magnitude of the earthquake by some independent means, and then we can measure features like surface rupture length or average displacement. So it's really important that in your mind you have the sense that a 10-kilometer rupture probably is about a magnitude 6, and then a magnitude 6 would probably produce about 10 centimeters of surface displacement on average. Likewise, you could say, well, a 100-kilometer long rupture is more than a magnitude 7, maybe 7.3, and a 7.3 would have 1 or 2 meters of surface displacement. So it just really, I think, helps calibrate your thinking when you think about what a single earthquake might do versus multiple earthquakes in terms of displacement. But also, so much of the time when we're doing our mapping, we're thinking about, well, how long was that earthquake, or what is the size of fault that might break? And so then we use these kinds of relationships. You can see they're really almost just order of magnitude as far as, okay, well, if it's 100 kilometers, we're thinking about a 7. So, so that was, I think, important, and it may address some of the questions that were coming up.
We probably will read this paper later in the semester.
Good. So here's kind of another classic paper. This is from Schultz, 1988, but we sort of call it the standard model for continental shear zones. And so the idea is on the left is depth, which is really measured in temperature, because that's what controls the behavior of the fault zone. But then given different geotherms, that would be certain depths. So like, you know, a lot of times we think about sort of about 30 to 35 degrees C per kilometer. So a critical transition is about 300 degrees C, which would be about 10, 11 kilometers, like in California. And that's because, as you can see, you know, this left column sort of sketch here shows the behavior of the materials, where we're sort of really having brittle behavior in this upper zone down to about 11 kilometers or so. And pseudotacholites, like frictionally generated melts. But below that, then we get this kind of onset of quartz plasticity. That's the key why it's 300 degrees C. And below that, we start to get more ductile behavior. But sometimes earthquakes can punch down into this zone. So that's why these black lines are here, the pseudotacholites. So we get sort of high strain rate frictional melting still. And then we go on, and there's sort of the frictional behavior of the fault. This sort of middle zone here is showing that when it's negative, it means that it's sort of velocity weakening. So that means once it starts to slip, it gets weaker and weaker and weaker, and we sort of have this catastrophic thing that's an earthquake. But when it's positive, it's velocity strengthening. So the faster it slips, the stronger it gets. And so what's key for us as we think about the deformation of the upper part of the fault zone is we're sort of dealing with this kind of slightly more passive and strong material that's sort of breaking by being driven from below. So that is just something to keep in mind as you know, because as we map, we're sort of looking from above. And so any of this material, we want to infer what happens at depth. We care about big earthquakes, but it has to be sort of filtered through that shallow material. So any questions so far? Comments?
Nope.
So the other thing is discontinuity. So, you know, these faults aren't planar, and you can think of them as being as stepping sort of in map view. So in this case, this fault steps to the left, so we'd call that a left step. But you can also have steps with depth, and so and these kinds of discontinuities are what produce all the interesting things along all faults. But we see them really well in strike slip cases. And here's a mixed one where I sort of joke, it's like the hood of my my truck, where it has like this bump on the hood for some, you know, space for the engine. But if you flip it on its side, it's this bump that then if you slide material past it, it drives a lot of extra deformation right in that zone. And because there's not enough room, it either is going to make a zone of enhanced compression and shortening, or if the sense of motion is different relative to the step over, it's going to cause dilation and opening, and that'll also have interesting effects. And so, you know, these kinds of discontinuities have strong influences on how the fault works, but also when we look at the topography along the fault zone, it has strong influence on what we see. So then if you think about sort of going from, you know, the top of that Schultz model through these discontinuities in the upper few kilometers, then we start to deal with this kind of distributed shear zone at the Earth's surface. And that can be a narrow one like this, which, you know, keeps things simple, or it can be more distributed. And so this is probably more likely. Of course, it's more complicated. And we'll probably read this paper, the Johnson et al. Paper, which is a really interesting one. But again, it sort of shows that filter, how we're going from the fault zone at depth through these discontinuities to shear zones at the Earth's surface. And obviously, if you have one earthquake, you shear at one time. But if we have repeated earthquakes, we're sort of building the shear zone, building the topography of the fault zone. So one way to look at this, and one thing that's been very influential in thinking, is experimental work. And so this is kind of a classic called clay cake. So it's a cake of clay that had a slit in the material underneath it. And as they sheared it, you could see the sort of, this is a kind of left lateral example. Early on, you know, A to B, you just see distributed deformation. But then by about C, we start to get these discontinuous en echelon faults forming, not exactly parallel to the fault zone, but sort of en echelon oblique. And then as the shearing continues, we get this sort of coalescence of the faults and linkage. And so this is topography. It happens to only be 10 centimeters and there's no erosion. But when you think about strike slip faults, this is kind of what you want to have as a model in your head. So here's now I have so then just to have definitions, we have this sort of step overs where, you know, you have to think about which way the material is moving along the faults relative to the steps. So in this case, it's a right lateral fault with the right steps. We get a basin or a zone of extension if in that arrangement. And then over here, we go right lateral with a left step. So if I'm walking along the fault, which way do I have to look for the other fault? To the left. If I come this way, it's the same way. So right lateral with a left step causes uplift or convergence. So obviously if the fault is left lateral, then the sense switches. So a simple strikes of fault that has no discontinuities isn't that interesting. But as soon as we get these steps and bands, which we know exist, even in clay, we start to get all the exciting topography. So any comments or questions so far? Okay, so I made here's just a few more cool videos. This is from our colleague Michelle Cook at UMass and some of her students. So we can just watch this for a few minutes.
We're here at the physical modeling lab at UMass Amherst. I'm here with Kevin Tenenbaum. So Kevin, can you tell me what it
Whoops, I was going to ask if you guys could hear okay.
Physical modeling is
No.
used to allow us to study natural processes that occur over time scales and length scales that we can't observe in any other way. So today we're going to be modeling a strike slip fault system. So we'll be growing our faults in a wet kaolin, and it's a clay, it's a wet clay, and it has the consistency of about Greek yogurt.
Okay, so you can grow faults in something that's the consistency of yogurt?
Yeah, so we can actually see little fractures and then slip along those fractures and create faults.
Do you want to tell us like what this is, what we're standing
So this
next
is
to?
our deformation box. So we grow our faults in this. We first pour the clay. We can either pre-cut faults or not, and then we can displace the box, and that displacement will grow faults.
Okay, so one side of the box moves, and then you say, oh, there's a fault, and then you take this ruler and you measure it.
So not quite. We use these high-resolution digital cameras to record the entire process, and then we use particle imaging loss symmetry to analyze displacements on the surface.
So now we'll just see a few videos of some of their experiments. There's no audio for these, but you know, it's just, I think, useful to get the intuition. So this is color showing strain rate. So in this, you know, sort of modern example, these experiments, we see, you know, sort of different characteristics of the fault zone depending on how the experiment was set up. And you want to sort of imagine different sort of ideas for how the earth works. So here's a bend. And what they wanted to show was they had cut the underneath the green zone was where the fault was kind of predefined. But what you can see, let me pause it for just 1 second, is some of the secondary faults that grow. And then around this bend, what you want to look at, the lower plot sort of showing the slip rate at these different locations. And so, you know, what looks relatively simple, like a simple bend, actually has a very complex evolution in space and time as the faults get kind of grow and then evolve. So let me just rewind this for a little bit so we can.
Was that a right lateral slip?
Yeah, these are all right lateral. You can tell, see the top is moving to the right.
Mm-hmm.
So in this case, this is a 10-degree restraining band. So they cut underneath in the box the what's underneath this green line, the high strain zone. But this fault here is naturally forming in the material. So the bend sort of enhances the contraction. In this case, it's the right lateral. So it's a restraining bend. Now, so then here is the one that shows the slip rate variation. And so you can see these two outer ones, the green, the red and the black, kind of stay steady, but the inner ones have some evolution in their rate of motion. And then even the red sort of got ingested into the bend as the bend grew. So just a couple more. This one is convergence. So they're sort of pushing, not only they're shearing, but they're sort of pushing the two walls of the thing together. And what you want to see is the green would be sort of shearing, but once you start to get some purple, it means it's really contraction or almost like reverse faulting. And so, whoops, what I wanted to show there was, oh, that's annoying that it jumped. Okay, let's just look for a second longer. what it was starting to show was that you have localized what they call kind of strain partitioning. So we'd have the main strike slip fault zone, but then adjacent to would be more pure contraction, and that can be local or across the whole system. And it looks like my computer is freezing right now. Let me just restart my PowerPoint. Anybody have any questions?
I have a quick question, Ramon.
Yeah.
In relation, in those contractions, especially in those videos, would those be, like, if we're looking at a fault zone, would those be considered part of the fault or separate of the fault?
Great. Well, it's a zone, so we would say they were part of that fault zone, but it, yeah, and you want to think of them, they're sort of linked mechanically, so they're working together. So you would think of them together and try to map them. You know, in some cases, these secondary faults can be quite far away. Like there's examples from Mongolia, from earthquakes from the 20th century, where the secondary part of the rupture was like 10 kilometers away, but we still think they were linked, although that could be somewhat debated. So let me just keep going. But I put the link for these videos so you guys can watch it maybe when it won't crash your computer. So just some definitions. I talked about this a little bit already, sort of contractional or restraining bends versus extensional releasing. And they can kind of be true steps or just bent faults, but they tend to, sort of bend versus step over, tend to cause similar sorts of effects. And then this is from the Davis and Reynolds textbook. I always think it's kind of funny because it's like a catalog of every possible thing you could see. So just, again, it's not like you don't have to memorize these things, but you want to start to have in your mind like all the possible patterns that you might see at different scales that then might drive some of the surface response that you end up mapping as far as the geomorphology.
What was this from, you said?
This is from Davis and Reynolds Structural Geology textbook is where I got it, but it's from this Journal of Structural Geology paper by Young-Sung Kim. So the reference is right there. Okay, let's look. Okay, so then what I've been showing is sort of 2D, but obviously you can have sort of 3D discontinuities, and those can have some interesting kind of patterns at depth. So we typically think about strike slip faults as having this kind of inward dipping superficial faults that kind of go to the master fault, and so they have this sort of flower petal arrangement, and so this is sort of classically called a flower structure. And it's a convenient model. We don't always see it that often. It's probably oversimplified, and obviously it can kind of vary along strike, but you can have, as they showed here, the sort of negative flower structure, so something that's a little bit more extensional or transtensional, or a positive flower structure, something that's a little bit more transpressional, driving some uplift. So these are quite complicated because you can imagine, well, which one of these traces is carrying most of the strike slip motion versus which ones are kind of more secondary reverse or secondary normal sense of motion that are kind of accommodating that strain complexity in the step over. So again, kind of textbook patterns that might stick in your head as you start to look for these kinds of patterns as you map. So questions? Okay, so let's talk about San Andreas for a bit, and then I'll hand it over to Rick.